Okay, good morning, everyone. I'm happy to be back. Sorry about Friday. I think I caught a bug from my son who got it from his school, but I'm over most of it now, except for my horse sore throat and hoarse voice. Anyway, luckily we have covered all of the material that we need to for EE 321. Today's class will be very short. We are going to look at chapter 5, which is computers, which is basically looking at all the building blocks that we saw in chapter 4 and how it is organized into a computer system or a computing system. So, all right. You know what? Actually, before I begin chapter 5, so announcements about the quiz. Be one more quiz. I'll make it open for Tuesday and Wednesday. It'll be based on the second half of chapter 4, which is logic circuits. And since we are very close to the final, I will not assess logic circuits, meaning chapter 4, separately on the final exam. So we have one more quiz, which again, I will open up tomorrow morning from 8 o'clock till Wednesday midnight. And that quiz will be based on the second half of chapter 4, logic circuits, and it will not be assessed separately on the final exam. Okay, so final exam will be chapters 1, 2, and 3 for the most part. Let's see what else. In case you're wondering why we finished up this early, is because most, I think except for quiz 1, all of the other quizzes were offline, meaning we didn't take up class time. And since it's about 5 quizzes, which is about close to 2 midterm examinations, that's 2 entire lecture classes. And so we finished up early. We progressed faster through the material. That's the reason why. Okay, so computers. All right. This is a simplified version of a computer architecture. A computing architecture, meaning a system that can work for computational purposes, has a logic unit that performs mathematical arithmetic functions. Hence the name that we give it, it's called ALU, Arithmetic Logic Unit. Okay, it performs the basic mathematical functions that are required in a computing system. When you have an ALU, it interfaces with a lot of external peripherals. Well, external in the sense it's external to the ALU itself, the unit itself, okay? Primarily being memory, the ALU unit needs to access memory in order to store and retrieve data functions while it's performing the computations. Then there are input and output devices, meaning our keyboards, mice, displays, monitors. Those are input and output devices. To keep all of it controlled and all of it connected, we use physical wires. These wires are known as buses because they transport information between the ALU and the memory and the IO devices. Okay, literally these are nothing but wires that carry signals. And by signals, I mean electrical signals, voltage and current. Okay, these are known as buses. Depending on how many bits can be transferred in parallel, we say that that architecture has 4-bit, 8-bit, 16 bits, 32 bits, or 64-bit, right? The most common ones in consumer electronic devices or consumer computers or consumer computing systems used to be 32-bit, and now we have 64-bit. That is, this refers to the size of the bus, meaning how many data bits can be transferred in parallel. Okay, that's the size of the bus. Literally, a 64-bit bus simply means the system has 64-bit architecture, 64 wires transmitting that information. And since we have these disparate units, everything connected and operating independently, we have a control unit that controls everything. And the control unit, along with the ALU, is the main engine that drives that computing system, known as the CPU, the central processing unit, more commonly known as the processor of our computing systems, right? The processor that we use in our computing systems. Now, the ALU, the arithmetic or the logic unit, basically comprised of the logic circuits, the building blocks that we studied in chapter 4. Okay, when EE majors take these classes, we go in depth and they study this for an entire academic year on how to use the building blocks and convert it into an ALU. All right, inside the central processing unit, we have, depending on the architecture, the central processing unit needs to interface with, as I said, memory. The memory, again, can be split into two different kinds. There's the volatile memory and the non-volatile memory. Volatile memory is the RAM chips that we use in our computers. Non-volatile memory is the EEPROM, and I've covered this in the previous couple of classes. The name RAM comes from the way the memory was addressed and accessed. Okay, so it's random access memory, but the name is kind of irrelevant in modern times. Okay, it's not random access memory versus EEPROM. It's basically volatile and non-volatile. Volatile memory simply means it requires power. As long as power is supplied continuously to that memory chip, it'll store the information that is sent by the CPU. Non-volatile memory does not require power. Okay, it is programmed and the program stays on there without any interruption. Modern times, even with that, it does require a little bit of power just to keep it getting refreshed all the time. So as a real life example, let's take a laptop or a desktop. If everybody heard of the sleep modes, that you shut the lid of a laptop, goes to sleep, right? Mac users, there is no option to prevent it from going to sleep. You turn the lid, you close the lid, goes to sleep. Windows, you have control. You can either keep it on or you can keep it off. You can put it to sleep or you can not put it to sleep. So there are options in Windows machines where you can close the lid of the laptop and still keep it on and not go to sleep. When a computer goes to sleep, what it does is it takes a snapshot of everything that is open at the time, everything that the CPU or the computing machine is working on at the time, and it stores that snapshot in the RAM memory. So the RAM memory requires power, right? So as long as power is being supplied, meaning if your desktop computer goes to sleep, it still has to be connected to the power outlet. Power still has to be kept on. For a laptop, power comes from the battery. So you put it to sleep, it consumes a little bit of the battery power. So if you leave it to sleep for like 15 days, your computer battery is going to get drained because the amount of power that is required, even though it is less, the length of time over a period of time, all of that battery power is going to be drained. Okay. Non-volatile memory, where we actually store the where we store the startup programs, which is the firmware of the main board. Even though it does not require continuous power, there's still some amount of power that is required to maintain that memory. It refreshes every once in a while. And that is provided by the coin cell battery that is on the main board itself. So if you open up any laptop or if you open up any desktop, the main board of any desktop will have a coin cell. It's a 3-volt coin cell. Some numbers are 2032, 2033, etc. And that coin cell can keep running for years, 8 to 10 years. Even if the desktop power is gone, the settings that are stored in the startup software in Windows, it used to be known as BIOS, BIOS, Basic Input Output System. Anytime you change the settings in there, it would be stored in the memory, and that memory would be backed up with that coin cell. Once the coin cell runs out of power, you have to replace it so that the memory is refreshed. Anyway, so that's non-volatile memory, and volatile memory is the RAM memory. Going on a bit of a tangent, in Windows machines, there is another setting called hibernate. The difference between sleep and hibernate is that hibernate does not require any power, or it requires very minimal power. And that's because it takes the snapshot and it stores it in memory and also stores it on your drive, on your hard drive or your solid state drive. So even if the power is disconnected, the computer state is frozen and it's stored, and you can, when you turn it back on, you can resume your work from that point on. So there's sleep, there's hibernate, and both of those use the memory features. All right, coming back to our slide here. So you have the CPU. The CPU connects with the different kinds of memory. It sends the information, stores it in there, accesses it, and then stores it, retrieves it as needed. Then you have the I/O peripherals. The I/O peripherals, you have lots of digital sensors, analog sensors, peripherals that can be connected to your computing system. And so when you connect these peripherals to your system, depending on the kind of sensor you have, you need to have a converter that can convert between the two forms, analog to digital or digital to analog. And these are simply known as A to D and D to A converters. So depending on what kind of sensors we are using, we need those kind of converters. And then, of course, everything is connected to the CPU via the bus. And the thing that keeps everything synchronized, because they're all independent systems, we need them all working in a synchronous fashion. We have a clock, internal clock, that synchronizes the CPU and the rest of that system. And the frequency of this clock is the frequency of your processor, is the speed of the processor. Okay. Modern times, the minimum speeds that we see nowadays in processors is about 2 gigahertz. 2 gigahertz. In the desktops that we're using, I think have processors that can go up to 4 gigahertz. Most laptops will run at least at between 2 and 3 gigahertz speed. Okay, it's 2 billion cycles a second. Obviously, the faster it runs, the faster it can perform its operations. All right, any questions? Hey. So computer systems are machines. Machines do not think, they do not know what to do. We have to tell them what to do. As humans, we need to interface with these machines, okay? So the earliest methods of interfacing with these machines which by the way is known as a language, machine language. Machine language, meaning you tell the machine what you want it to do. And then machine language, the lowest level is known as assembly language programming. Assembly language. This is the lowest level of programming. When we talk about levels, and when I say lowest level, meaning the lowest end is the machine, the highest end are the humans, at least until Terminator comes into action. So machines are the lowest end, humans are the highest end. All language programs are somewhere in the middle. Okay. If we talk directly to the machine, we have to use languages known as assembly languages. And we literally use numeric keypads to type in instructions. So when I was a student, way back in the 90s, early 90s, we worked on 4-bit and 8-bit processors, 16-bit processors, and those we learned assembly language programming. It is still in use to this day. Anytime you have a machine, not something that's for a very specific purpose that is part of a larger machine, we use assembly language programming to tell it what to do. Again, it only needs to do one thing. It needs to do one thing over and over and over again. And those kind of machines, we use assembly language programming. So we literally use hexadecimal codes. We type in 8C, 9F, and we tell the machine what it needs to do. So assembly language programming is the lowest language. And at the highest level, we are human programming languages. Anyone hear of BASIC programming language from a long time ago? That's also in the language that I learned a long time ago when I was a student. So we had those languages, and then we had C, C++, object-oriented programming, and nowadays Python is really big. Okay, in fact, if you the computer science department, CPE and CSE and SE students, they have to take introduction to computing program, introduction to computing as a CS 101 or CS 100 level course. And they teach Python in there. Okay. So I had C plus. Python has become really popular right now, especially with like data science. It uses Python language. It's very easy to use, very easy to understand. But that's not my wheelhouse. I'm not an expert in programming languages. But from what little I know, and from what all the other people, general opinion is that if you learn C programming, then you're well set and you can learn any other programming language with ease. Okay. So if you are interested, you should definitely, perhaps many of you already know some of these programming languages, but if you are interested in learning something new, I would suggest you start with C and Python, and then go on from there. Let's see. So these are high level languages, meaning we humans can write in words, in the English alphabet, in the English words that we use. There is a syntax, there is a grammar that is associated with each of these functions. But you write the program in this higher level language and then translate it into machine language by something known as a compiler. You say you compile your code. Compile your code means it takes the human programming code and converts it into assembly language and sends it to the machine. Okay. So computer systems require computer programs. Programs can be done in low level as well as high level languages. Then we have computer systems have CPU registers. Registers, as the name suggests, and I pointed out in the previous classes, it stores data, it stores memory, and so it's used to actually store and retrieve data while processing. Okay. Something also known as interrupts. And interrupts is basically a CPU is tasked with doing multiple things at a time. So depending on the priority, there's something known as interrupt, IRQ, interrupt requests that a CPU receives from multiple peripherals at all times. And the CPU prioritizes which task it needs to do first, which it needs to do second and third, and so on and so forth. Sometimes we don't have need for a very powerful system, right? Central processing unit, powerful computer, a standard processor made by Intel or AMD, or those are the two big ones. Okay, those are the two big ones. That's the x86 architecture that we use. Intel was the founder of the x86 architecture. Okay, for a long time, Intel was the only one until AMD split away and started doing their own thing. At the same time, there were processors that would work with reduced instruction sets. Okay, reduced instruction sets. And actually, you know what? Let's talk about instruction sets later. A microprocessor, a standard microprocessor, which we just know as CPU or as a processor, can do millions of things. Okay, it can do millions of things. It can handle millions of tasks, millions of instructions. Okay, the instruction code set is very large. Okay, it's very large. But let's say you have a machine that needs to do only one thing over and over again. Putting a very expensive processor in such a machine is pointless. If it only needs to do one or two things over and over again, there is no need to put a powerful processor in its place, right? So those times we use something known as a microcontroller. Okay, so it's a very simplistic way of defining a microcontroller versus a microprocessor. A microprocessor can do various things. Microcontroller can do very few things, more efficient. It doesn't require a full-fledged operating system to actually run that microcontroller. So microcontroller is very similar to a microprocessor in the sense that it can also do computational things, but it's limited in the instruction set that the instructions that it can perform. Microcontroller, like a CPU, can interface with external sensors, both analog as well as digital, can be interfaced directly to these microcontrollers. There are operator inputs. Then there are displays where you can actually display your output or send your output. Okay, so I was talking about reduced instruction set, right? Reduced instruction set. So microprocessors typically have a very large instruction set. Microcontrollers typically have a very reduced instruction set. Okay, they can do limited things, but they can do limited things very well. So a reduced instruction set computer is known as RISC, RISC. And one of the biggest names in RISC machines is ARM. It's a small British company whose products are now used, whose architecture is now used in pretty much every mobile and every mobile device nowadays. Anyone heard of ARM? ARM? ARM stands for Advanced RISC Machines. It's a British company and developed this architecture that can be licensed by other companies to create their own CPUs. Every single architecture that we use nowadays in mobile devices is licensed by ARM. So last few years, you've heard how Apple has moved from like Intel processors to their own processors. Well, it's not technically their own. They license the architecture from ARM, and then they use that architecture to design, to create their own designs. Qualcomm is a big, is another big company. They license ARM architectures and they create their own processors, and they sell those processing designs, to other vendors worldwide. Samsung uses ARM. Pretty much NVIDIA uses ARM. Every other company that actually develops their own CPUs or processors uses the ARM architecture. Okay. Apple did, I think, go one step further. They licensed an architecture for their exclusive use, and so they now use those processors for their laptops and their desktops and their professional machines. Again, that's a whole different thing. But again, none of these companies actually make their own microchips. They only design their own microchips. They only make their own processing units. I mean, they only design their own processing units. They do not fabricate or do not manufacture their own microchips. That's a whole completely different thing. Anyway, so a RISC machine is a reduced instruction set computer. And there is a very famous microcontroller chip made by Advanced Technologies known as AT328P. Okay, ATmega 328P. It's shown right here. It's a 28-pin microcontroller. Yeah, excuse me, 28-pin microcontroller. This is what it looks like. For those of you who are in the classroom and I come into the lab, I have Arduino boards here that actually use that AT328-pin chip. Now, this is the actual packaging. The actual chip is probably this size, very small. Okay. Everything else is just packaging. So it has external pins to make connections to external sensors. It has analog voltage references. It has digital input pins, digital I/O pins. It has analog pins, reset, and then there are connections of ground and power supplies. There are two separate power outs. There's a 3.3 volt line. There's a 5 volt line on that board. Now, microcontrollers, there are hundreds of microcontrollers in existence, okay? Every year, every company's come up with a new microcontroller, okay? Microcontroller chip, microcontroller board. Every time they come up, they have to, engineers would have to learn the language and learn how to program every single microcontroller, okay, when it comes. So there was a, I'm just going to a little bit of history, talking about the Arduino project. There were a couple of guys in Italy sitting at a pub sometime late in the evening. And as most things happen, over a few drinks of beer, they came up with this idea to get people involved and make microcontrollers and microcontroller programming accessible to the masses in a very simple and easy way. So they came up with this idea of taking this 28-pin microcontroller chip and creating a board that could be used for prototyping hardware and software projects. They named it after an Italian king, a medieval Italian king known as Arduino. Hence the name Arduino. It's become very, very popular. It is used for many high school projects, many college level projects. The audience for that is, high school students, working professionals. We have a class here at Cal Poly that is a GE course that teaches you how to use microcontrollers and create projects using Arduino as well as other microcontrollers. It's EE322. It's a GE course. I believe it fulfills upper division B or some requirement. Okay, it's EE322. Anyway, so they came up with this idea. It's become very, very popular nowadays. It's very common. You can buy pre-built kits with like various sensors and resistors and diodes, transistors, DC motors. Pretty much half of the lab kit that we use in 361 is included with the Arduino kits. And you can check out these Arduino kits right here on the bench when you leave. It has a USB interface. You take the Arduino, you connect it to a desktop computer, and you write a program in C language, which is known as sketches. And there are pre-programmed functions. Okay, so you do need to know a little bit of programming, but that's the point, right? Students or people who want to learn can take these boards with very minimal instruction. They can have their own program up and running in a matter of minutes. Okay. And what you can do with this is only limited by your imagination. There are large libraries of high-level functions that are available. There are various temperature sensors, pressure sensors that are available. During the pandemic time, I created a hands-on course where students would be in their own residences, and they would have a Arduino kit of their own. And I created a set of experiments that students could do hands-on learning in their own residences. So if this is something that you would like to do, Arduino kits are available online for less than 30 bucks. It comes with a breadboard, wires, sensors, kits. You could be busy for like, quite a few months. It's a very quick and easy way to get into programming, and it's also a fun way to get into, electronic projects. So these are some of the projects that we did. We had a input program and a code that I provided the students, connected a LCD display to this Arduino, and you can type in your code and you can display whatever messages you want. You can do whatever functions you want. So we did a few separate functions where we used the Arduino as a voltmeter and then interfaced digital and analog sensors to it, temperature sensors. And so it would measure the humidity, the temperature, and display it on the LCD display. In fact, I actually did have it's right here. I had a program running temperature measurement with a temperature sensor on that Arduino. So again, that's a microcontroller. It's very, very popular. There's also, again, there's a huge community out there, worldwide community that people come and share their projects. So if this is something you would like to explore further, there is a class that is offered in the EE department. It's a GE course. But if this is something that you want to do on your own also, it's not that expensive a hobby. You can buy these kits, from Amazon, from online vendors, and well, you can learn something on your own. Then there's Raspberry Pi. Raspberry Pi was a endeavor. I think again it was a British endeavor that was again started as a means to encourage students and attract students from a young age and to get them involved in hardware and software programming. Okay, it's based on the Broadcom chip BCM2711. And Raspberry Pi is a lot more than the Arduino microcontroller. The Raspberry Pi can be run as a full-fledged computer. I mean, because of the size of the CPU and the size of the memory that it can store, you cannot run like a Windows operating system on there, but it can do much more than what a simple microcontroller can do. Okay, this is not my wheelhouse though. Raspberry Pi. I wanted to get into Raspberry Pi for a while, but I haven't had the time to actually sit down and learn it myself. And then lastly, I just wanted to talk about system on a chip, SoC. SoC is another word that you may have seen thrown around in modern mobile devices. And SoCs are so called because it incorporates a lot of the external devices onto one single chip itself. So if you take a laptop or if you take a desktop, more often than not, it will have the RAM memory separate, the modems that is used to communicate with the outside world is separate. More often than not, the graphics card, the graphics chip is also separate. The last 5 to 10 years, actually last decade or so, Intel and AMD started integrating their display chips inside the CPU itself. Okay. In mobile devices, it's even more important because of the lack of space in a mobile device. You take your CPUs and your GPUs, graphics processing unit, and it's all combined onto one single chip itself. And hence, it is known as a system on a chip, SoC. So most mobile devices nowadays have the CPU, the GPU, the memory, and more importantly, the modems that it needs to communicate with the outside world, all on one single chip. Okay, all on one single chip. And those are known as SoCs. By the way, Qualcomm, headquartered in San Diego, leads the world in modems since the time of, well, since a long time ago. It holds the patents, most of the patents that is developed for modern day communications. Okay. And so even though companies can design their own processors, they cannot design their own modems. It's not easy. Qualcomm is the expert in this. Their engineers have this tradition, this history, and of course it carries on. And so even though Samsung, Apple, Dell, they all design their own chips, they still have to pay licensing fees to buy the modems from Qualcomm. That is also one of the reasons why most of the Samsung phones sold outside of Korea use Qualcomm chips and Qualcomm SoCs rather than their own. If you buy a Samsung phone in Korea, in South Korea, it uses their own processors, but the modems are still purchased from Qualcomm. Anyway, the reason is because Qualcomm is the leader in 4G, 5G technologies. So this is a synopsis of, again, it's the bare synopsis of what a computing system would look like, okay, digital computing system. And that is the end of chapter 5. As I said, it's a very short class for today. All right, questions? Any questions at all? Well, okay. We'll say the class is at an end. I will be available. I'm in my office and I expect I may not be here tomorrow, but I probably will be here on Thursday also. I'll be here on Wednesday, but this is the last class. Okay, so there's no class on Wednesday. I will be here. I will be working. I will be available in my office via email, via Zoom. However you want to see me or contact me, I'll be available. Final exam on Friday during class time. Final exam is in person. There is no online option. Every student must bring their IDs. Most of the students who attend class in person, I know them. I know their faces. I know their names. But many of the students are online. And so there is to verify everybody's IDs, I will require everybody to have their official Cal Poly IDs. And you will sign in and sign out. All of this information is on the final exam page. So please review the final exam page. Quiz tomorrow, Tuesday and Wednesday is on chapter 4. Again, I'll post the announcement offline, not proctored live. If you have any questions, reach out to me. And then chapter 4 will not be assessed separately on the final exam. Chapter 5 will not be assessed on the final exam. This chapters 1, 2, and 3. Diodes, op amps, transistors. Yes. So question being asked is about practice exams. So there is no. The only thing I would say is if students do the homework and the quizzes, you'll be fine for the final exam. Okay. review the homework problems, review the quiz problems, and that reminds me, I need to write out the solutions and post it. So I'll have them on the class notebook, hopefully sometime later today or tomorrow. So you do the homework, review the homework problems and review the quizzes, and you'll be good for the final exam. Okay. It will not be anything like, whoa, what is this? We've never seen this before. It won't be anything like that. Okay. It's a 2-hour exam. I will design it for an hour and 15 minutes or hour and 30 minutes. The students will have plenty of time to actually complete it in time. Let's see what else. Any other thing? Yes. No, it's on paper in person. The question being asked is about the final exam format. It's in person. It's a paper-based. It's a paper-based exam as a regular normal exam. Okay, so I will hand out the questions, answer sheet, and then you return it back to me. And students will sign in and sign out, meaning you sign in first, get the exam, and then when you sign out, I will not accept an exam from a student unless they sign it in front of me, unless they sign out in front of me. And I will explain this again on the day of the exam also. It should be on the final exam page also. Okay. All right, other questions? Yes. Yes. Yeah. Well, I'll talk about that when all the lab students are here. Any other questions? Well, it's been great teaching this summer. I actually enjoyed it a lot. One of the downsides, of course, is having multiple modalities is that in-person attendance is always low, but that's kind of like the downside, but that's fine with me. So I enjoyed working with you all. Those of you are online, those of you are in person. Again, I apologize for the last few days. But yeah, I'll see you on the day of the final, if not. Okay. Have a good day, and I will, well, see you all later.